This is the 10th video in my series on three-phase power transformers. In this video, I'll be looking at the per-phase equivalent of a Y-delta connected transformer. You can find out more on this subject in my course entitled Electrical Three-Phase Power Transformer Fundamentals. You can access this and my other courses on my Stan Store at this web address. I'm switching back to the voltage diagrams here because I want to develop a per-phase equivalent circuit for this type of transformer. The phase relationship on the primary side, we've already discovered that the line-to-line primary voltage is equal to root 3 times the line-to-neutral voltage on the secondary, and that the primary line-to-line voltage will lead the secondary line-to-line voltage by 30 degrees, giving us the equation there. And I can rewrite that equation just taking the line-to-neutral voltage primary on the left-hand side and putting it all equal to the voltage line-to-line all over root 3 at 30 degrees. Now, in order to find out what the turns ratio is, I could take the line to neutral primary voltage and put it over the line to line voltage on the secondary, and that would give us the turns ratio of each of these legs of these transformers. And I'm going to rewrite that equation such that the voltage line to neutral on the primary is equal to A times the voltage line to line on the secondary. Now, as I said, I want to develop a per-phase equivalent circuit. So in starting to do a per-phase analysis, we have to work with Y-connected sources and loads. So we have to convert all of our delta sources and loads to Y connections. So I'm going to develop a hypothetical neutral on the secondary side because there isn't one, but because it is a balanced system, I can develop a hypothetical neutral for the secondary. And there is a phase relationship associated with the secondary and this hypothetical neutral, such that the line-to-line voltage of the secondary is going to be root 3 times the line-to-neutral secondary, and it is going to be leading the line-to-neutral voltage by 30 degrees. This is a phase relationship if there is a three-phase system with a neutral, which we've hypothetically developed. Now I'm rewriting the equation, bringing the voltage line to neutral over to the left-hand side. That's all I've just done here, and bringing all the rest of the terms to the right-hand side of the equation, giving us this final equation here. Now, in developing the per-phase equivalent circuit, I'm going to take these two equations and I'm going to divide one by the other. And I can do that mathematically as long as I do the same with the left-hand side of the equation as I do with the right-hand side of the equation. So if I bring the left-hand side of the equation down, I've got the voltage line to neutral all over the voltage line to neutral, primary to secondary. Now I have to bring down the right-hand sides of the equation and do the same thing with them. A voltage line to line all over the fraction that you see there, voltage line to line secondary, and that is all over root 3 times 30 degrees. Well, I can make this a little bit more simple simple by bringing the denominator of the denominator up onto the numerator, which I can do mathematically. And that will get rid of at least one of the division signs and make the equation a little bit easier to work with. Now you can see that we have a voltage line-to-line secondary in both the numerator and denominator, so they can cancel out. And again, I'm going to replace the a root 3 with a primed, and that gives us the equation, the primary voltage line to neutral over the secondary line to neutral, a primed at 30 degrees. And I'm going to rewrite that equation right away because I want to use it in this other fashion. The voltage primary line to neutral is equal to a prime, the voltage line to neutral secondary at 30 degrees. And that tells us again that the secondary lags the primary by 30 degrees, which we already knew. Now, I want to bring down a couple of terms and equate them to the line to neutral voltage, but I want to do it using the line to line values. And I can do it by this fraction. And you might say, well, where did we get the numerator and denominator from for that fraction? Well, these two equations tell us that the primary line to neutral is equal to the numerator, and the voltage line to neutral is the denominator. We've already developed that, so I just brought them down and put them one over the other, which is equivalent to the voltage line to neutral over the voltage line to neutral primary to secondary. And I'm just going to make that fraction simpler by moving the denominators around, and I'm left with this equation, which has a common element in both the numerator and denominator now, which we can cancel out, and that leaves us with the primary line-to-line voltage over the secondary line-to-line voltage is equal to the voltage line to neutral primary all over the voltage line to neutral secondary, and both of those are equal to a primed at 30 degrees. And I can rewrite the equation again, and this time it's the voltage line to line primary is equal to a primed, the voltage line to line secondary at 30 degrees. Now you might have been wondering why in our black box that I drop down and say the secondary lags the primary by 30 degrees, and you might be wondering why I left off the voltages and the currents, or whether we're talking line to line or line to neutral, because it doesn't matter whether we're talking about the voltages line to line or the voltages line to fictitious neutral line to neutral, or the currents in the primary secondary. They all lag the primary by 30 degrees if it's a Y delta connection. We now have enough equations to establish a per phase equivalent circuit. And we use the formulas for voltage, line to neutral primary, line to neutral secondary, as our per phase, because we're talking about a balanced system here, so we can look at one phase, do the analysis, and then extrapolate it back to a three-phase quantity. So our single phase equivalent circuit would look like what we have there on the left-hand side of the slide. And the primary voltage is line to neutral voltage, and it's equal to A primed times the line to neutral secondary voltage, but it's leading it by 30 degrees. So our equivalent circuit tells us that if we wanted to calculate the line to neutral primary voltage using the line to neutral secondary voltage, we have two operators that have to operate on that voltage. One is a phase shift of 30 degrees. We'd have to add 30 degrees to it. And the second operator is the turns ratio that we'd have to operate on the line to neutral secondary voltage. So we'd have to multiply by A primed. And we have established what A primed is. It's the actual turns ratio of the transformer times the root of 3. Now, we've already established this equation for the secondary line current in terms of the primary line current, and these are phasor values. So if we wanted to look at the primary line current in terms of the secondary line current, we'd have to divide by the operator and we'd have to add 30 degrees. So our operators would look like this. In going from the primary side to the secondary side, we would have to multiply the primary voltage by the turns ratio A primed. However, the phase shift doesn't change. We still, going from the primary to the secondary, we would have to subtract 30 degrees because the operator has not changed. In other words, if we were going from the secondary to the primary, we would have to add 30 degrees. So you remember our black box that says the voltages and currents are shifted the same by 30 degrees. So there's no difference between the shifting of the phase of the voltage or the current. However, the turns ratio is inversed. This video is part of my Electrical Technical Information series. In this series, I'll be covering essential topics to help you understand electrical systems. Be sure and stay tuned, as I will also, from time to time, be reviewing electrical products that, in my opinion, are worthy of paying attention to. Some of those products include 𝐃𝐈𝐒𝐂𝐋𝐀 big and small standby generators. This is the best time to try out any of 𝐃𝐈𝐒𝐂𝐋𝐀's products because they are having a huge sale starting April 4th and lasting until April 21st. Here are just a few of their products, starting with the 𝐃𝐈𝐒𝐂 Delta Pro and Delta Pro Ultra and the Delta 2 Max, including the River line of smaller standby generators, the Delta 2, the Wave 2, the Glacier, and the River 2 Pro. The River Pro, the River 2 Max, and the River 2. And a range of portable solar panels, including a 400-watt portable solar panel and a 200-watt bifacial, and the Glacier. And finally, a unique product, the Wave 2, which is a portable air conditioner / heater that fits anywhere. To obtain more information on this subject, simply fill out the information requested when you go to this website. Before I end this video, I want to repeat the connection to obtain my free copy of the Ultimate Guide to Residential Standby Generators and receive access to the major April sales on many of the 𝐃𝐈𝐒𝐂 products. Also, here's the connections to obtain a free copy of my 50-page electrical power crib sheets. And finally, here's the link to all of my electrical courses, which are located in my stand store.